Hello. Today I am going to be explaining this AP Physics test question. It looks something like this. And so first I'll read the question. So one end of a 1.00 meter string is attached to a 0.72 kilogram mass. The other end is attached to a hook located 1.25 meters above the floor. The mass is released from rest, theta1 equals 31.6 degrees, and allowed to swing without friction. As the mass reaches the bottom of the arc and begins to swing back upwards, the string is cut. So right here, the string is cut when theta2 equals 14.8 degrees. Calculate the horizontal distance from the point directly below the hook to where the mass lands. Air resistance can be neglected. So first, we want to write down all our givens. We know that theta1 is equal to 31.6 degrees. Theta2 is equal to 14.8 degrees. Let's see. Length is 1 meter, the length of the string. We know that the total height is 1.25 meters. We know, and then we know that the mass is 0.72 kilograms of the ball. So next we want to figure out what type of problem this is, so we can figure out what set of equations to use. And if you're listening closely, you would have noticed that, or if you see the question, it says that, where is it? And allowed to swing without friction. So what this tells us is that friction can be neglected. And so there are two sets of questions sets of equations which we could use. There's the conservation of forces and conservation of energy. What the sentence that says swing without friction tells us is that we can neglect friction. Friction is negligible. There's no friction, and that tells us that we don't need to account for it, which tells us we don't need to use the summation of forces and conservation of forces equations, telling us we can use the conservation of energy equations because those are a lot easier to use. You don't have to do as much. And so, we also know initial velocity is 0. So then we use our conservation of energy equations. So P, potential energy plus kinetic energy equals potential energy plus kinetic energy. And we know, I guess we'll write these equations out first. So mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. And this is because we know that within a system, energy cannot be, all energy is conserved. Energy cannot be created nor destroyed within a closed system. So we know that the system is at rest to begin, is initially at rest. So we can cancel out our first kinetic energy because V equals 0, which would take out that term. And then we know, so there are two things that we have to find. We know gravity, we know mass, but we don't have height and velocity. So that's what we have to try to figure out first. And we just have to look at the problem and see, okay, so we know the ball will be at 2 points, here and here, and we know an angle. So immediately, angle, trigonometry. And we can make two triangles, one with theta1 and one with theta2, based off the x reference axis. So we'll say okay, we know our hypotenuse is 1 meter because that's the length given. We have theta 1 equals 31.6 degrees. So we'll do the first triangle first. And then we know, that's it. That's all we know. So now we have to figure out what h is. So, and then we can see that the component along the x-axis, x-reference axis, is related to cosine. So now we have cosine theta, theta 1 is equal to, we'll just call this a for now, a over 1. So we know now a over 1 because the hypotenuse is equal to 1. So now we know that the height along here, right here, is equal to cosine theta, this length. Let me write this out. This length right here. This length right here. And so now we know height is 1.25 minus that. So we say mg multiplied by 1.25 minus cosine 31.6 is equal to mg. Now we have to do the same for the other triangle. So we say 1.25 mg multiplied by 1.25 minus cosine, what was it, 14.8 degrees. All right. Oh, I'm missing the parentheses. Plus our last kinetic, because there's obviously kinetic energy as the ball is in motion. So we have 1/2 mv squared. And what we're trying to solve for is v. So we have everything else. We just need to solve for v now. So we can cancel the m out, and then everything goes onto one side. So we want to isolate v. So we say 2g multiplied by 1.25 minus cosine 31.6 degrees minus distribute 1.25 minus cosine 14.8 degrees equals v squared. Okay, and now we want to root the whole thing. So v is equal to 1.50 meters per second. And that gives us the v of final as the ball is swinging. But now we have to figure out what the velocity is, or now we have to figure out displacement. So we figured out what this exit velocity is as soon as the string is cut. And so now we just have to figure out this displacement. So now we know that we can use the vertical displacement equation, because you can see we know initial velocity, we know acceleration in the vertical sense because it's just gravity. And so now we need to figure out time, because time is the only thing that's missing for us to use the kinematics equation delta x equals v initial t plus 1/2 at squared. And all we need is time. So in order to do that, we can solve for time using the y reference axes instead of x. So delta y is equal to our initial velocity. I'll write the equation out. V initial 1/2 at squared, right? And then we just have to plug in what we know. So delta y is equal to our 1.50 meters per second t plus 1/2 1/2 gravity squared. So 9.81 over 2 t squared. Now we have to figure out, okay, what is delta y? Well, delta y is just y final minus y initial. And now because we're separating this into two parts, so now this is our y initial. So delta y is equal to 0 because the ball lands and stops. So we can say 0 minus, and then we know this height from our earlier triangle, 0 minus 1.25 minus cosine 14.8 degrees. Now this is equal to our little quadratic, 1.5 t plus 9.81 over 2t squared. And now we can just solve as if it's a quadratic, but one very important thing that I forgot to mention earlier is gravity is actually negative, which is really important when you solve the quadratic because then you get I and stuff. Because gravity is going downward, so it's accelerating in the negative direction. And if you wrote your reference axes like you're supposed to, you would see plus y is going up, but gravity is forcing us down, which is negative. So it's really minus 9.81 over 2. I forgot about that. That's my mistake. And yeah, that's one of the small things that you just kind of have to watch out for. So now we can do our little quadratic. So move everything to one side, and then you have t equals negative 1.50 plus or minus the square root of 1.50 squared minus 4 times negative 9.81 over 2 multiplied by 1.25 minus cosine 14.8 all over 2 times negative 9.81 over 2. So now, if you do a bunch of, calculations in the math, then you'll get t equals 0.438 seconds. You'll get two answers, but one will be negative, and you can't have negative time. So you're obviously going to pick the positive one. And then so now we have time and we have initial velocity. So now we know, okay, you have your delta x equals v initial t plus 1/2 at squared equation. We know acceleration is constant, so we can just cancel that term out. And then we have delta x equals v initial t. And you just plug in what you have. And so that gets you, what is this, 0.438 multiplied seconds. Don't forget units because it's important. Make sure they all cancel out correctly. And now you have 0.658 meters. That's it, right? No, it's not. Because if you look at the problem, it's not asking for delta x when the line is cut. It's from delta x from the hook to the to where the ball lands. I could have drawn that a little better. Let me draw that a little better. X. So then you just have to add your little triangle. So it's just 0.658 plus cosine 14 point, not cosine, sorry, sine 14.8. which will get you if my calculator wants to work, plus sine 14.8. And there you go. Where did my pen? So delta x equals, or no, I should say x. X is equal to 0.913 meters. And there you go. That is how you solve this problem. I think the main key takeaway here is to, when you look at the problem, think about if you want to do conservation of energy or conservation of forces. That's number one. And then break it down so it's not overwhelming. I think, yeah, problems like these, you just got to break it down into simpler parts, and it's all simple. See, it's just conservation of energy, which we can do, and then kinematics. That's all it is, motion in 2D. And yeah, that's how you solve this problem. Thanks for watching. Subscribe and like.